Alright, we're going to continue with our work of motion, and we're going to look today at motion without resistance. So, in the last lesson we looked at motion and particles moving in a straight line, and the equation of motions were given in the question. In this lesson we're going to look at questions where information is given in the question about force or acceleration, and we have to find the equation of motion. Okay. As I've mentioned before, the greatest difficulty in solving mechanics questions comes from choosing whether we want to v dt, d by dx of a half v squared, or v to v dx. Again, we've got this little diagram that I've talked about before. You can refer to this for any confusion. Okay, a couple of things that I'm just going to quickly mention in this video, but we would have talked about this a lot in class, in Newton's laws. So Newton's laws underpin much of our work in the rest of this chapter, and much of the work that we've already done in projectile motion. Now, knowledge of these laws allows us to do unusual questions, and they ended up being a lot easier. In this mechanics topic, it actually is quite an easy topic. It just can be overcomplicated with the words, but if you're using these laws, it really, and you understand these laws, it really simplifies what we're doing. So his first law says that unless acted upon by a resultant force, a body remains at rest or in uniform motion. That just means the body's going to continue moving or continue being still unless something changes that. Number 2 is the acceleration of a body is proportional to the resultant force, blah, 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 blah. That just means that F is equal to ma. We've all seen that before. F is equal to ma. And last one, for every action there's an equal and opposite reaction. That's also going to be quite important here. Okay. Just want to get straight into the questions because we talked about all this in class, and these videos are just mainly to have a look at the questions. Okay. So example number 1. I've got a particle of mass m is moving in a straight line under action of a force. The force is equal to I don't know what Greek letter that is. I think it's omega. I'm not sure. Let's just go with it being omega. Omega m x plus 2, where omega is a positive constant. Well, given the particle starts from rest, prove that v is equal to the square root of omega x squared plus 4x minus 12. Let's again draw a diagram for this question. So we've got a particle, and again it's moving in a straight line, so we can draw a diagram really easily, helps us imagine what's happening. So we're told that it starts at x equals 2, and it starts from rest. So that means initially, the particle starts at rest at x equals 2, so that means its velocity is initially 0. Okay, now we've got moving in a straight line. We don't necessarily know the direction it's moving in, but we do know that this is a positive constant, which is kind of implying that it's moving this way. So let's write it is. So force is equal to, I don't know if it's omega m x plus 2. Okay. Right, and we want to know, we want to prove that its velocity is this at some point in time. So we've got some x, and the velocity is something. We don't know what it is. Now we know F, the force, is equal to omega m x plus 2. Now this is where we're going to really use Newton's laws. If you're stuck, you're going to go back to this. Newton's law tells me that F is equal to ma. But in extension 2, in maths, we don't like to say acceleration, we're going to say x double dot. So this is going to be our Newton's second law. That's very, very important here. Force is equal to m x double dot. We're going to replace it with that. So m x double dot is equal to omega m x plus 2. Okay, obviously our m's are now going to cancel, so x double dot is equal to omega x plus 2. And the question wants us to prove we've got something with velocity being the subject in terms of x. If we think of our tables of values, we're told that whenever my acceleration, where's my table of value? Whenever my acceleration is a function of displacement, I'm using this one, and that's going to be important. So here, this is our acceleration, x double dot, and it's a function of displacement. So we're going to replace it with d by dx of a half v squared. And that's equal to omega x plus 2. Okay. Let's have a go at integrating both sides. So integrate this, integrate this. No matter what conditions we add here, it's still going to cancel out. So we're just going to take that integral there. But we are starting at 2 and going from x. Now you don't have to do this step here. All this step is doing is eliminating finding the plus constant c, but it ends up getting the same answer. If you really want to be fancy here, you can say we're starting at rest, so integrating from 0 to some unknown velocity. So it's going to be a half v squared from 0 to v, which just gets you a half v squared minus 0. And that's equal to, integrate this. Now omega is just some constant, so omega, and then we've got x squared on 2 plus 2x from 2 to x. Okay, so we've got a half v squared is equal to omega, and that's going to be x squared on 2. We simplify this. I'm just going to do it quickly. X squared on 2 plus 2x minus 6. We want to cancel out that half there, so v squared is equal to omega x squared plus 4x minus 12. Take the square root, and I believe we're done. Omega x squared plus 4x minus 12. Okay. The second example we're looking, and this is again where the diagram, it can look really confusing, and if you think about it too much, you're going to overcomplicate it. You just want to look at your diagram, add in the basic information, and have a go. They're honestly not that difficult. As we look at these questions, we're going to think of the idea of tension. Now, tension is the force that a string needs to pull up something. So without it breaking, this tension is the force the string is using. And it always acts, if I've got, for example, object A and it's got a downwards force of mg, well, the tension is always acting this way. It's always acting kind of against the movement, and the movement is being pulled down by this gravity force, and the tension is going in the opposite direction. So if we have a look at this example, so particle A has a mass m kilos, and particle B has a mass of 2m. Now we're always thinking about forces. Tension is a force, so the force that's going down is F is equal to ma. Now the acceleration in this instance is gravity, and the mass is m. We have a look at this one, the mass is 2m, and the acceleration is still gravity, and tension is moving up. Very important thing is that if you have a closed system, which means a system in this instance that's got a single string, the tension, no matter where you are on the rope, is going to be the same. So we've got connected by a light, inextensible string. That just means it can't be stretched. Is that realistic? No, but it makes the maths easier. Again, on a frictionless pulley, is that realistic? No, but it makes the maths easier. Initially, the particles are at rest. After particle A has travelled x meters in the upward direction, it is travelling at v meters per second. Now we have to think about this as a closed system, which means that anything happening here is affected by this, and anything happening here is affected by this. Now we can see that the whole system is going to be moving this way, and that's because particle or object B, mass B, is heavier. So this one's going to be moving up, and that one's going to be moving down. So the system's going to be moving this way. Now we know that F is equal to ma, so F is equal to ma, or mx double dot. Now the force of the whole system, we think about it as one single system. The mass of the system is going to be m plus 2m times by the acceleration. Now let's think about what's going to be happening here and here. Now the force right here, the force going down, is going to be the weight force going down minus tension. Tension is this force that's stopping it from snapping and going down. So the force that's going downwards is the weight force. Take away whatever force the rope is holding it up with. And it's the same idea over here. Mg minus tension. So the force that's pulling it down, but it's not dropping and falling to the ground, there's a tension force that's subtracting that weight force and making it lighter, so it's not moving. Now this system is going this way. It's going this way. So the force is going to be, well, initially, if we forget about this weight here, the only force we care about is this one, and it's being pulled down, 2 mg minus tension. We're told that the system is moving, and this force is pulling it down. But there's a force that's opposing it being moved down, and it's the weight of object A. If object A wasn't there, B would fall much faster. So the downwards force, we need to subtract this force here, which is pulling B upwards. And it's not literally pulling it upwards, but it's stopping it from falling down as fast as it normally would. If there was no mass here, then this would fall a lot faster. So the force going down, this force here, is being subtracted from this force, which is pulling it up. Okay, so that's 3m x double dot is equal to, the tensions will cancel, so we get mg, which means x double dot is equal to g on 3. Okay, now we want to know, we want something that has x in it and velocity. Now we don't have x or velocity in this. Now importantly, this g is a constant gravity. Realistically, gravity isn't constant, but for the simplicity of our calculations in this question, it's going to be constant. Right, so we want something that involves velocity and x. Whenever we have that, we're using d by dx over half v squared. Integrate both sides. Now we're going to integrate here. We're initially, we're told the particles are initially at rest, so from rest to some unknown velocity, we're integrating here. Initially, we've travelled no distance, and we want to know an equation for how far my velocity after x distance. So this is going to be a half v squared is equal to g on 3x from 0 to x. Of course, that's just going to be a half v squared is equal to g on 3x. Times it up, we get v is equal to 2 on 3 gx v squared, and square root both sides. I'm pretty sure we'll get to the answer, 2gx on 3. Let's check. Right, that's what we're trying to prove. Okay. Example number 3, they love to have these inclined planes questions, and try to forget how you were taught these in physics, because physics doesn't teach these very well. A 100 kilogram box sits on a slippery ramp which is inclined at an angle of 30 degrees to the horizontal. If the box starts from rest, find its velocity after t seconds. Again, we're drawing a picture for this. Really, really helps visualize what's happening. You don't have to, but it really does help. So we've got some sort of box is sitting on a ramp, and it's 100 kilos. Now, we're going to have a look at some forces. We're going to resolve some forces here. This is going to be my force of gravity going down, and it's going to be its mass. Remember, F is equal to ma. Its mass is 100 kilos, and the acceleration is gravity. Okay, and we want to know the velocity of it going down the ramp. I'm going to just extend these lines because we're going to have to do a bit of manipulation. Now, if you've done physics, you're going to know that sign is involved in this question, but let me prove to you why. So that's going to be our force going down. Now, this is our normal force. The normal force is the force that, well, we've got our force. The box is exerting a force on the plane going downwards, and the normal force is just the force that acts upon it. This normal force is stopping the box from falling through the ramp, because by Newton's third law, it tells us that every reaction has an equal and opposite reaction. So this force is the force that the box is exerting on the ramp, and Since it's not braking and falling through the ramp is exerting an equal but opposite force in this direction. This is my weight force down here, and we want to know the force going down the plane. Now we could extend that right here and say that this force here is my force going down the plane. We maybe add that in like that. So that's going to be my force down the plane. Now we know that this is equal to 100g. We've already discussed that that's the weight force going down, 100g. And we want to know this force here, which is the same as this force here. Now over here, this is going to be 90 minus 30, which is 60. And then this is a right angle here, so that's going to be 30 degrees in there. And if we call this the force we're after, we call it force D for force down the ramp. The force down the ramp is going to be 100g sine 30, because this is the opposite, that's the hypotenuse, and the value of the hypotenuse is 100g. So it's 100g sine 30. From here on now, you can just accept that's true. The force down the ramp is sine. The normal force, this one here, is cos. Okay. Now, let's replace our force with mx double dot. We're always going to be doing that. Mx double dot. We know that the weight in this instance is 100. So we've got x double dot is equal to, the hundreds cancel, and now sine 30, I believe, is a half. Let me quickly check. Yep. So we've got g on 2. Sine 30 is a half. And we want to know the velocity after t seconds. So we want a function that has velocity and time. So we're going to replace it with dv to t equals g on 2. And we can probably integrate this however we want. You could flip it upside down and get time, but it's probably going to be easier just to say, okay, let's say that this is equal to dv, and that's equal to g on 2 to t. Now we're going to integrate from some initial velocity, which is, I assume, rest. We're told, yep, we're starting at rest. So from 0 to some unknown velocity v, and we're integrating from 0 to some unknown time t. These correspond with each other. If we started at 1 second, then this would be 1. So integrate nothing, we get, or constant, we get v is equal to g on 2 t from 0 to t. And I think I've missed a, no, so yeah, we get velocity is equal to gt on 2. Okay, that's its velocity after t seconds. Now we want to know its displacement after t seconds. So we want a displacement function. Now we know velocity is dx to t, and that's g on 2 times t. We can just integrate both sides. So integrating, we're initially starting at 0, and we're going to x. And again, we're initially starting our time at 0, and we're going from some unknown time t. That's going to get us x is equal to g on 2 times by, what's that going to be, t squared on 2. That should be a t squared on 2 there. So t squared on 2 minus 0. So the answer is going to be gt squared on 4. Yeah, there needed to be a t squared on 2 there because I'd already integrated. Okay. Last example for today, we've got a body is projected upwards from the centre of the Earth with an initial speed u. The acceleration due to gravity at any point on its path is inversely proportional to the square of its distance from the centre of the Earth. That's telling me that gravity is no longer constant, which does make sense. The further you get away from Earth, or the centre of the Earth importantly, the less gravity is going to be. We've got let the radius of the Earth be r, and the acceleration due to gravity at the surface be minus g. Okay, let's draw a picture. So we've got the Earth here. Now the distance from the centre to the surface of the Earth is r. Now we're moving upwards And we initially start at the surface of the Earth, and our velocity initially at the surface is u. Now we do know that we've got some acceleration going down, x double dot at r, so my acceleration at the surface of the Earth is minus g. And we know that the acceleration anywhere else, we're told it's inversely proportional to its distance from the center of the Earth, from the surface of the Earth squared. We're told to define x. We're going to say x is the distance from the center of the Earth, because this says inversely proportional from its distance from the center of the Earth. So x is my distance from the center of the Earth. Okay. So we know that the acceleration of the object anywhere, no matter where it is, but we're told it's inversely proportional to the distance from the center of the Earth squared. Now we know that at the center of the on the surface of the Earth, when we're told that the acceleration is minus g, so my acceleration on the surface of the Earth is minus g, and the surface of the Earth is a distance of r from the center of the Earth. So that's going to tell us that k is equal to r squared g, or gr squared. So we now can replace our x double dot with our value of k, so we're going to put k there. So minus g r squared on x squared. And we want to know, we've got velocity in terms of x. So we're going to use d by dx of a half v squared. And that's equal to minus g r squared on x squared. Let's have a go at integrating this. Let's just remember that these are constants here. So let's take the indefinite integral maybe of both sides. So a half, did I leave more room for this? No. V squared, integrating both sides. We're going to get, what, that's going to be minus g, oh, we'll change to blue, minus g r squared. If we integrate minus 1 on x squared, actually the negative is going to cancel, and we're going to have positive 1 on x plus c. Okay, I might insert a blank dotted page here. So I've got a half v squared is equal to g r squared on x plus c. Now we want to know what this constant c is here. We do know that the initial speed is u, and that is at a distance of x is equal to r. So a half u squared is equal to g r squared on r. That's because the initial velocity is u at the surface of the Earth, and the distance from the center of the Earth is r. That's because we've defined x to be the distance from the center of the Earth, plus c. So a half u squared is equal to gr plus c. Which means that c is equal to a half u squared minus gr. Okay. Then we're going to substitute that back up into here. Okay. But we're going to replace our c with a half u squared minus gr. Alright, let's get rid of that 2 now. So this 2, we're going to times this up. So we've got v squared is equal to 2gr squared on x plus u squared minus 2gr. Okay, so here we've got 2gr squared on x. What have we got? Plus u squared minus 2gr. Thinking we want to factorize a 2gr out, so u squared plus, what's that, 2gr. Now we look at where we're trying to get to. there's an r squared here, so it's looking like we are going to have to take out an r squared. Now, if we take out r squared, 2gr squared from this, we're just going to get 1 on x. Minus, if we take out r squared from this, we're going to have to put a 1 on r there. And that's actually what we wanted to prove. All right, thank you.